Hi everybody, my name is Kyle, and today we're going to do Redis 101, Getting Started with Redis. Redis 101 is designed to take you from no knowledge of Redis all the way up to using some of our more advanced features. So my name is Kyle, I am the head of developer advocacy here at Redis Labs, and I've been using Redis for a long time, and I hope that I can impart my knowledge to you during this training session. So, what is Redis? This is a question that I get sometimes when I'm talking to people at conventions and things like that. Redis stands for nominally Remote Dictionary Server. Now, Redis has been around for about 10 years. I've been using Redis since about 2012. But on our 10th anniversary, I was interviewing Salvatore Sanfilippo, the guy who created Redis. He's available online as Anti-Res. But Salvatore was talking to me about this, and I said, Redis stands for Remote Dictionary Server. And he said, that's not the whole story. In fact, Redis, when he was creating the name for it, he wanted something that had 5 letters and an available domain name. So in some ways, Redis is a bit of a backronym. So you can see that in the original domain name that he did buy, which was redis.io. And this is actually one of our leading sites as far as being able to give you information about how to use Redis. Well, before you start using Redis, you have to know what Redis does. It's an in-memory database platform. In-memory is the key value here, is a key statement here. And in-memory basically means that we store natively in memory first. And it's a database because it can store things and retrieve them in interesting ways. Redis, like I said, you can find all the information at Redis.io, but Redis is open sourced. And indeed, Redis.io is open source, so you can actually do pull requests on it. But Redis.io provides all the information about the commands. Now, one of the neat things about Redis is it's written in really clean C code. So if you don't find what you want to know about Redis and one of the commands and how to use it, just head on over to the GitHub repository, and there you can see exactly how it's written. It's written really simply, and you can see exactly how everything's implemented with just a simple number of simple searches. So it's BSD licensed, which really means that you can do what you want to with it, right? So let's go ahead and take a look a little deeper into how Redis fits in. Now, Redis fits into the database landscape in kind of an interesting way. One of the things that people think of when they think about a database is this idea of a relational database. You have tables, and those tables have schemas which define how the columns store, and there's rows in those columns. And then if you want to make a change to how those columns are stored, you have to do what's called a schema change, and it's really kind of painful. But that's what people think of when they think of databases. They also have this ability to relate different tables together, right? Now, on the other end of the spectrum, of databases, you kind of have this idea of a pure key value store. Pure key value stores basically store data with no relationship between anything else, right? This is just kind of this collection of data that is out there. There's no structure to it, but you're able to retrieve it in a fast way and replicate it and do all the things you'd normally do with a database. So they're kind of polar opposites. Now, Redis is not a pure key value store. It kind of sits in between these two ends of the spectrum, and has data structures, and we're going to get into that in just a moment, which really define how things are stored in the database and how they're retrieved, and the commands in which you can use them. So it's really kind of an interesting part of the spectrum of databases. So let's dive in a little bit further into those different building blocks or data structures. Redis has a number of built-in data structures, and in fact, it can be extended. There's other parts of the trainings that talk about modules, which add different data structures to Redis. But here we have these different structures, and we'll talk about them all. Now, starting up at strings, the red Lego brick in one corner, this is the most fundamental data structure in Redis. This basically stores data, and the data can consist of a few different things. It can be numbers, it can be numbers 1, 2, 3 stored as character 1, 2, and 3. It can be strings, so hello, my name is Kyle in ASCII characters or Unicode, or even binary data. And so these are what we call Redis strings. There's a few derivatives of that. We have bitmaps. Now, we've talked about Redis being in memory, and what that means is that you have the ability to arbitrarily flip bits in the data. Because we are in memory, we don't have to worry about sectors on a hard drive or any of that stuff. So you're able to arbitrarily set those bits, and you can represent things that way with those bits. So if you need to really store a lot of compact, let's say, data flags, this is the way to go on it. Another derivative of strings is the bit field. Going down the list here. Bit fields are like strings. They are actually the same data type, but they're manipulated in different ways, just like bitmaps are. But they allow you to arbitrarily put different size integers in, either signed or unsigned, at an arbitrary position. So let's say you want to put in a U32 and then a U48 and then a U16, so unsigned integers of those sizes, and then followed by a signed integer of 6 bits. You can do that, and you assign numbers to those and retrieve those back out at arbitrary positions as well. So it's really great for doing things that would require a lot of compact number storage if you already know the data types. And then shifting gears entirely, we have hash maps, or hashes. These are a collection of fields and values stored at a single key. So you can think of it as kind of analogous to a row in a table without any structure implied to it. Pretty easy. Then we have linked lists. And linked lists are this idea of having a series of, it's actually doubly linked lists, elements that has connections to the following element, in both backwards and forwards. What that fundamentally means is that you can add things to the end or beginning very easily. So if you need to add something to the start of a list or add something to the end of a list, that's very easy. But if you want to manipulate or change something in the middle, it's quite problematic because you have to traverse each one of these. But it's really great for storing ordered things without having to actually store them in any kind of timestamp format. Now, moving up to the other column, we'll talk about sets. These are this idea of mathematical sets. So if you've ever done set theory or anything like that, where you're talking about unions and intersections, this is kind of that fundamental type. How Redis represents that is a series of strings. So you have this idea of those strings being represented inside a general set. So you can easily check for membership as an example. So is this element in a set, or this member in a set? So member is how we have what we have in sets, series of members. So a derivative of that is actually the sorted set. And sorted sets have all the same properties as sets, but they add a index to them that allows for sorting. So this would be kind of like a score. That's what we actually call them. So you have members, the scores, and sorted sets. A further derivative of sorted sets is a geospatial index. Geospatial indices are this idea of being able to plot things on the globe and be able to find things in a given radius, as an example, or the distance between 2 points. So you kind of have to think about things in latitude and longitude. And then we have hyperlog log. Hyperlog log is a probabilistic data structure, probably the most esoteric built into Redis. But what this data structure does is estimates cardinality. It's kind of similar to a set in that you can, you're storing things in, it doesn't restore repeats, but it can easily estimate the cardinality of the unique items in a given hyperlog log. So without actually having to store all of the things completely. So you can store practically an unlimited amount and then estimate the cardinality in only 12 kilobytes of space. It's a really kind of interesting data structure. And then finally, the newest kind of member of the data structure family in Redis is the stream. And streams are kind of interesting. They are a series of hash map-like objects, so fields and values, stored in a time sequence order. So this allows you to have items that are coming in at a given time inserted into it, and then it'll have field values inside of it. What's cool about it is it has a lot of metadata associated with it that allows you to actually use it for different services in a microservices architecture, for example, to write to, and read from different services and be able to kind of keep a consistent place and be able to process items off of it. So it's really handy for that sort of thing. It can also be used in place of a hash map in some cases. But today we're going to be talking about just a few of those data structures: strings, hashes, lists, sets, sorted sets, and geospatial indices, which will give you a lot of things to do. Don't worry. So how do you get up and running with Redis? Now, this is something that you'll have to do anytime but now. Today we have a set of pieces that are designed for you to be able to do this. It's called our learning environment, our app assembler. That is available to you, so you should have information on that. But if you want to do it at home on your own machine without the app assembler platform, then what you're going to need to do is follow these instructions. On Linux, you can easily install it with whatever the kind of package manager you have on Linux, apt-get install redis-server, for example, in many different flavors of Linux. In macOS, you can do something similar with brew, which does kind of the same package manager type of roles. If you run Docker, which most platforms do have some sort of Docker support, you can do Docker run Redis, which is quite easy to do. And If you're on Windows, you have a couple options. You can either use Docker, just like we did in the previous point, or you can use the Windows subsystem of Linux, Windows Subsystem for Linux, I think is what it's called, WSL, and do it just like you would in a Linux install. And then if you don't want to do any of those things, Redis Enterprise Cloud Essentials is a service that Redis Labs runs, which is my employer. And we offer free instances of Redis as long as you keep on using it. It's 30 megabytes for life if you are continually using it. If you stop using it, we won't keep it running, obviously. But you just go to redislabs.com and sign up for that for free. So you can get started right now on it. So a few options for you. Now, interacting with Redis on a day-to-day basis, you're going to probably build an application that will work with Redis, but you will probably need to also manipulate things in Redis from time to time. So the first thing you need to do is probably start getting familiar with Redis CLI. That's what we'll be using in this session. This is a command line activity where you're actually typing commands into the Redis CLI process, which then communicates with Redis. It's great for those who are, command line whizzes, right? If you're not one of those people, we have a GUI available. It's called Redis Insights, and it's available at the URL on the screen. And this is basically a process that runs on multiple different platforms that allows you to kind of manipulate things in a more graphical format inside your browser. So very handy, and it even has support for our modules, which we have other opportunities to talk about those in the rest of training. All right, how do you dig into Redis? Let's talk about a series of problems. Now, the first problem we're going to solve for is caching, and we'll talk about further problems later. Caching is this basic idea. You've probably seen it before, where you have a slow database or multiple database calls that are created for a single web page, and then you need to make sure that gets sped up. How do you do that? You can use Redis strings. They're really kind of perfect for this. You have the command set, which allows you to save data as a key value pair. And you can retrieve that value back out of it by specifying the key with get. You also can store strings, text. In strings, you can store text, numbers, and binary things. So anything you can get out of a database, we can pretty much store. But the real difference is the superpowers that Redis has. Redis has a number of superpowers that enable caching to be really easy. All keys have the ability to be expired. So you set an expiry up, and then after a while, that key will disappear. And then you can set that up so maybe you don't want to keep something around for a long amount of time because it may become stale. You can set that up inside of Redis itself. You can also register for key changes. So in that case, when one key changes, you can have an application listen, and then you can maybe change another key or delete something else. So you can kind of set up these different processes that will enable it to be really easy to do non-trivial things. And then we have the ability to do multiple eviction policies. Those eviction policies enable you to not have to worry about managing memory, and it will just evict things that are taking up space when you get to a full point. So moving forward, let's talk about how these commands actually look. We're going to be using the same format over and over again. And in this case, that format is going to start with a command. And the command is always the first thing in this kind of way we're displaying it. The second is the key name. In almost any Redis command, the key name is the first argument, okay, after the command. And then the second argument is the value in this case. So we have set user ID to 8754. So we're setting a number. Redis will respond with OK, and that basically just says I've done it. Now, if I want to get that value back out, I have my command, which is get, and my key name, which is the only argument here, and it will retrieve that value immediately for me. Then we have expire. Expire will actually go and retrieve that, or actually will set the expiry on that value. So user ID 1 says, I don't care about it after 60 seconds, right? After 60 seconds or thereabout, it'll go away. And then Redis will respond back with 1. Then we have unlink. And unlink is pretty simple as well. This actually removes data. So we're going to specify unlink as our command, and our first argument will be the key name. And it will respond back 1 that it's done so. Now, there's 4 different ways data kind of tends to go away in Redis. We're going to go from, my goodness, excuse me. Let's see if this stays on this slide. So the first column is when we're going to talk about unlink. So unlink here, basically, we're going to set up a number of scenarios. So this first column, I set foo to 1, and that's going to happen on all 4 of our columns. It's going to respond back, okay, so it's stored. And then I don't want it anymore. So I can then say unlink and then foo. When I try to get foo, it'll be gone. Now, the key thing here is that we're actually not freeing up the memory synchronously. Redis, the important thing to know about Redis, for the most part, it is a single-threaded server, which means that it can do one thing at a time. It becomes very important for other properties of Redis that we keep it that way, but it makes the code very easy to reason about. Now, I said for the most part. Here's where it changes a little bit. Because Redis is single-threaded, freeing up memory is actually not a completely free action. So if you want to deallocate something in an application, that takes some amount of CPU cycles to do so. And values in Redis can get quite large. In this case, we have like a single byte. It's no big deal. It'll free it up in nanoseconds. But let's say you have a value that's quite large, hundreds of megabytes. That actually might take some time to do so. So Redis has the ability to use unlink to remove that from the ability to be referenced. So it says immediately, I want to break the link between the key and the value. And then what I'm going to do is actually, in a separate thread, at some point in the future, I'll free that memory up. This is the primary way which you remove data in Redis, is with the unlink command. Now moving to the next column, we're going to do the same thing. We're going to set foo to 1, and then we're going to set an expiry of 10 seconds on it. So expire foo 10. All right, from back 1, that's successful. And then we're going to try to get foo. Okay, it returns back the value that we expect. About 10 seconds later, we try to get the value again, and it will say it's not there. Okay, so this is expiry. Okay, now when I say about 10 seconds, that's actually quite important. Redis, in most versions of it, the future versions may change, doesn't actually do it in the exact way. The reason is, let's say you set 1,000,000 keys to all expire in the same second or the same millisecond. We wouldn't want that because that would cause the single-threaded server to kind of spend a lot of time just removing data. So Redis uses a sampling method to actually go through and say, is there anything I need to expire here? So it does it quite quickly, and it can be pretty exact, but I wouldn't rely on it as a timer, for example. So it's about 10 seconds when you set an expiry of 10. Now moving on to the third column, we are setting something up in a very unusual way. We're going to set up Redis to have a very small memory footprint. You can set Redis to have an arbitrary memory limit, and in this case, I'm setting up to be very small, where I can only store one key in it, right? I'm going to store one key with 1 byte, so it's going to be as small as I possibly can set it. And that's in a configuration option. So I have this tiny Redis instance, and I set my foo value to 1, and it says, okay, I can do that. Also in the configuration, I set this up as what's called an LRU. This is an eviction policy called least recently used. So when I do that, basically it means that when I don't have room, I will evict the least recently used key. So I have a very tiny database here. The least recently used key here, I don't have any memory, will be foo. So I'll evict foo to make room for bar. So when I get foo, it's gone. But if I was to get bar, it would have 2 in it. Now finally, on the last column, this is where we're doing the opposite of the first column. This is where we're using the command del. Del is an earlier version of a command to remove a key. This does a delete synchronously. So as an example, if we had a value that was 512 megabytes, which is actually our limit on Redis for strings, it would spend all the cycles it needed to remove that value synchronously before it allowed any other command to work. That's why the memory freed between the column about del is at a different space. You can see it's synchronously doing that. So we get foo and it'll be nil, but there may be a delay because it's freeing memory. Now functionally, unlink and del are the same. So you don't have to worry about which one should I use. Most of the time, 99.99999% of the time, use unlink. It's more performant and it is just as easy. It's a very cheap optimization if you have something that's already using del. In some very small circumstances where you need to immediately remove that memory, del is a preferred option, but it's very, very small circumstances. Unless you're doing something with transactions, you're pretty much going to need to use unlink to achieve the best performance. Okay, now it's time for you to start looking at these pieces. So here is an exercise for you. After I explain this, you can go ahead and pause your video and use your environment to go ahead and do these through, and then we'll go over the answers here. So the first thing to do is to set your initials with a key user ID. So we're going to send like user ID colon, you see on the screen JTC, and then we have the kind of 6-digit representation of your birth date. You can do anything you want to, just a value, right? Then we want to get the value back out of user ID. We will expire it in 10 seconds. So use the command that would expire things. Wait for about 10 seconds to try to get the value back out again. And then set the same user ID with the value one more time. And in fact, you can use the up key in Redis CLI, and you can actually kind of scroll back through what you typed in before, just like at the bash prompt. We'll unlink that user ID, then try to get the value back out. Now, I have supplied to you on the other side of the screen a cheat sheet, and that cheat sheet will tell you all that you need to know. So you don't have to remember the arguments. You just kind of need to sub in the things as they make sense here. So go ahead and pause your video at this point, and we'll come back and we'll go over them. All right, let's take a look at this. Now, here we have the actual results. I did this myself, and so you can see what it looks like. Here I've taken and I've set my piece here that says user ID, and I set it to birth date. So that was pretty simple. Then we're going to get that value back out. Pretty easy to do again. We'll expire the value in 10 seconds. So we're using the expire command here, and we're getting that integer 1 back as our response. We'll get the value back out of it, and we can see we've waited 10 seconds, so it's nil. So there's about 10 seconds that's elapsed between these two commands. We'll set the value up again using the same that we did previously. And then we're going to try to unlink it, and immediately we'll see that it's not available anymore. So you can see the full life cycle here. We've added values, we've expired them, we've unlinked them. So it's a good starting point. Now, let's get into something entirely different. User sessions. User sessions are actually the #1 use case of Redis, believe it or not. People associate Redis with caching, but user sessions are actually a more common use case for us. But the reason sessions exist is this idea of trying to maintain state between different page views, right? Across multiple servers. Now, this basically is an artifact of having to expand beyond a single computer. So back in the day, when an application, a web application basically ran on a single computer, you could store this in memory on the machine itself. But now everything's behind a load balancer. So you may connect to server A and then server F and then server C in sequence. But if you've logged into a service, so anything that you put in a username and password, you want to maintain that kind of the information about the user. So this might be preferences or like a shopping cart or just that they're logged in. And you can specify those as session variables. So Redis actually provides hashes, which are a perfect match for this type of use case. We have hset, which will let you save session variables as key value pairs. So the key itself refers to the kind of session ID, and then the actually session variables are the name of the variable is the key, and then what's stored in the variable is the value. We'll retrieve those values back out with hmget, and then we'll use hincreby to increment any field within the hash structure. So let's say that you had a number that you wanted to kind of just say, I don't know what the number is, but just add 1 to it. We can do that with hincreby. And of course, we can delete something out as well. So in that case, maybe you have like an item in a cart or something along those lines that you no longer want. So you have hdel there. Okay, let's see how it looks. We have our initial 4 values we want to look at. They're in this table here. And we're going to populate this. And we're going to use hset for this. Now, hset is an interesting example of a command in Redis because it's what's called variadic. Variadic commands in Redis basically are commands that will accept a variable number of arguments. So it's not actually that complicated, but it can be a little overwhelming at first. Let's just go through it. The first is the command. The command here is hset. And then the first argument, as always, for most commands is the key itself. So we're hsetting to this key name we have here, and then we're going to alternate between fields and values. So if you look here, the second argument is the field, and the third is the value, and then the fourth is the field, and then so on and so forth. They go back and forth, just kind of alternating. And you can set any number of hash fields and values that way. So it's not something that you have a fixed limit. So in this case, I'm showing a small number of them, but you could have a smaller or larger number. Now, the return value here is 4. That's kind of interesting. We'll return back to that, what that actually means a little bit later in the presentation. So let's do another operation here. We're going to get those values back out, and we're going to use HMGet. Now, I want to let you know about kind of how these commands look. Why is it called HMGet? Well, the first letter of a command is usually the type that you're using. So in this case, H stands for hash. Makes sense. Now, if you ever see M in the second position, that generally means that it's a multiple. Hash, multiple, get. It makes sense. It's just shorthand. Our second argument here is, or excuse me, our first argument is the key, as always, and then we're going to go and specify, again, variadically, a number of different fields that we want to retrieve. Okay, so we're specifying 4 fields here, and we're retrieving those back out, and it's going to return them back in the same order which we requested them in. Easy enough. Notice that we're not retrieving the field names because we've already specified those. Redis is trying to save a little space by not returning those, or a little bit of time by not returning those, since you should already know what they are. Now, let's take a look at how we can increment something. We're going to use the command hincrby. Let's break that command name down. H stands for hash, incr is for increment, and by says I want to increment by a certain amount. So this is actually telling you how to do this. So we have a hash. We're going to supply that key that is a hash, and then we're going to put the field, which is the field we want to increment. We're incrementing it by whatever. In this case, we're incrementing it by 1. So hits incremented by 1. So if you notice, hits was a 1. We added 1 to it. It's a 2. Now, why is it a 2? Let's look a little further. hincrby, again, the same command, the exact same command. It's going to return 3. You probably put 2 and 2 together here, or 1 and 2, actually, to get 3. And what that actually is doing is returning back to you the value which it has just changed it to. So it was hincrby. It was 0, return 1, so on and so forth. So if we had 10 in the value and you hincr by 10, return 20. So very handy if you want to do something where you don't know the value of it, but you do know you want to increase it by 1, and then you don't have to do a separate set to retrieve it. So let's do something here where we're going to do hset, and the difference here is our field is something that we haven't previously defined. So last page is our field in this example, and we're going to set it to home page. So the return value here is 1. Okay, that makes sense. We've added something to 1. So maybe 1 is the return number we've added. Take another look at an example here. I'm going to do this and change last page to about. In this case, last page is already defined, so it'll return a 0. So in this, what it's actually telling you is, which ones that we've added, because we didn't add last page, so it returned a 0, right? But we did change it. So let's go a little deeper. We're going to get this last page variable back out, or the field back out rather, and it's going to return about. But let's say we want to get rid of it. We'll use hdel, and that will delete a field from the hash, and it's going to return back 1, just like unlink or del would otherwise. Okay, now it's your turn again. So what you're going to do is you're going to populate a hash with the table there that has user ID, first name, last name, ID, last visit. Increment the hits field by 1. And notice it's not in that original bit. So what happens here? Get the user ID, the first name, and the hits. Look at the value of those. Set the IP address to this new value, and then delete the last name. So go ahead and pause your video right now. I'll come back, and then we'll go over those answers. Okay, how was it? Should be pretty good. Everything is there right on the screen for you, so let's just take a look at it. Okay, so we're setting here. We have set user ID, first name, last name, and IP, and last visit to it's returning 5 back, right? So that's the number that we added here. Now, hits is not part of that, so we're going to do hincrby, the same key, hits 1, and since it was a non-existent one, Redis assumes that it's a 0, and will actually give you the value back as 1. So the new value of that field hits is 1. So then we're going to do hmget on user/2, user ID, first name, and hits, and then return them back in that order. And we're going to hset user sesh to IP. The IP was already up there, so it's returning 0, so we didn't add anything. And then hdel, we're going to delete that last name. It's going to return a 1. Okay, let's move forward. You can see how that we've explained all of these here. Okay, moving on. Managing queues of work. So let's say you have tasks that need to be worked on in an asynchronous fashion to reduce blocking times or wait times in your application. So these items may build up and you have lots of items to work on. You may need to assign to another process to remove items from the queue. And you have this kind of high-speed, low-latency requirement. This is where Redis really works well. Redis lists are ideal for this. You can use lpush and rpush to add values to the beginning or the end of the queue. And then you can use something like rpop lpush, pops an item off one queue and then adds it to another queue. Now, let's look at this example a little bit further. When you're talking about these type of things, what actually do you mean by queues? You know, a good example of this is in a new user flow when you're building an application. A lot of times you have to do email verification. Now, almost any service that sends email will take a while to do that. Even if you're directly connected to, you know, an email server, it may take a few seconds for it to actually confirm that it's sent. Not something you really want to do synchronously for your users, but you want to make sure that they get that. So this is a great option for queues. So in that case, what you would do, instead of actually sending the email directly, you'd add it to a queue, right? And then you'd have another process that's sending the emails and says, give me an item off the queue, and then I will process that. So that's a really more concrete example here. Now, another thing I want to point out here is something that kind of breaks what I just told you in the last block. Our commands here are lpush and rpush. Lists start with an L. So you might think that they all start with L's, but that's not actually the case. In this case, it's one of the earlier commands in Redis. We hadn't established the complete and total, like, you know, the first letter represents the type. So L or R both represents list. But really what we're doing here is talking about a linked list. And it's a doubly linked list. And I tend to think of lists as being kind of like one directional, and usually vertical is how I think of them. But we should think of them horizontally, right? So L push means that you have something on the left, you're pushing to the left, and R push to the right. So you need to think of them as kind of this horizontal plane of items, and you're pushing on to the left over here, onto the right over here. That'll help you explain what's going on with these commands. So let's give an example. We're starting with Q1. Now Q1 is not a key yet, and if you haven't gathered already, Redis requires no instantiation step for most operations. So we can just start working on something. So we have this empty list. We're going to do lpush, and we have a Q1 as our key, and we're going to add the value orange to it. So right now we have one element in the list, and it's going to return back 1. Now, lpush Q1 green. So we're going to push to the left of this, and we're going to have green there, and we're going to return 2. So we can see here that we're returning the length of the list. Now, rpush red. So this is going to add to Q1 red on the other side of it, and it will return 3. So you can see how we've done this. We've added different items to it. Now, as we look at this, we have one queue that we've already established, and we have this another queue that we're going to use. Right now, it doesn't exist. It's empty. So we're going to do rpush lpop, or excuse me, rpop lpush. Easy to get that wrong. It's a little unpronounceable, but basically we're taking 2 commands, an rpop and an lpush, and then mushing them together. You can do this in certain circumstances. This is probably one of the only ones. But what it does is actually enables you to take from one queue to another queue atomically. What do you mean by atomically? Atomically, in this case, means that we're doing it in an uninterruptible fashion. So it either works or it doesn't. So you can't have a situation where if you were to do these in 2 separate commands, you bring it rpop off of one and then bring it to your client-side application, and then go, we would push it into something else. If there's a failure in there, you have the ability to lose data. But rpop lpush is atomic, so there's no way to lose data. So it works or it doesn't, right? So in that case, when I run it, it's returning red, right? And that's the value that we have moved. But now Q2 has that one item off the other one. How does this fit into the example that I talked about with like that new user flow? So in that case, what you would be doing You have your application that's adding new users, and then you have your service that's going in and processing that. So instead of having to go and do two different operations, you're actually doing one operation. You're moving it atomically from one over, and then you're also getting that value back out. So maybe it's an email address, and then you start processing on it. So really cool how you can do that. It's just something that allows you to kind of easily build these kind of things that would otherwise be a little risky or maybe hard to reason about. So now it's your turn. In this case, take 5 minutes to do this. Pause the video after I give the explanation here. But what you're going to do is you're going to create a queue of 5 email addresses of people you know. Could be anybody. You can make them up for all I care. Remove the first element off the queue. Just kind of remove it off, and then atomically move from one element off the queue and add it to another in one step. So we have a cheat sheet here. We'll tell you all that you need to know. And go ahead and do this. And in just a moment, we'll go over the answers. Okay, how was it? I hope it was easy. Let's go over this. First thing we're going to do, we're going to use lpush to put those 5 email addresses in. It's returning 5, which is the length of our queue, our list. And then we'll use lpop to pop something off to the left side. So we're popping 5 at example.com off in this case. And then we'll use rpop lpush to move from my list to my list 2, and it's returning 1. So we're doing rpop, so we're popping off the right side and adding to the left side of my list 2. So all happens pretty easily. Okay, now let's move on and talk about something different. Building a recommendation engine in Redis. Now, I'll be completely transparent here. This is not how you build a real recommendation engine, but it does give you an idea of what you can do with it. This is vastly simplified from what a recommendation engine would normally be, but it's a digestible example. So let's say you have people reading an article on a news site, and you also want people who have read similar articles to kind of get this idea of what they might also be interested in. You don't want data mining. You want this to be real time. So if something happens in the news, it can be something that you can respond to immediately. You will see similar ideas with things like purchase recommendations. So somebody who bought, let's say, maybe a baby pacifier may also want to buy a baby crib. That sort of thing. Also identifying fraud. So in situations maybe you have, we know of fraudulent activity that follows a certain pattern. This might be helping you to identify that when you're building this type of recommendation engine. So we'll use Redis sets here. It's a great way to learn how to use Redis sets, a connection of unique strings. Let's look at a few commands. The first one is sadd. Sadd will add a tag to an article. So you have multiple tags or one tag that you can add to an article. Sismember to check if the article has a given tag. And then smembers to get all the tags for a article. So 3 things here. If we notice, they all start with S, just because they are set operations. And then smembers is actually something we'll talk about in kind of the last portion of that. This represents something that is also in other commands that we need to talk about a little bit as far as computational complexity, but hold that thought for now. And then we'll actually talk about sinter or set intersection to find some more articles tagged with the same tags. So how does this look? Sadd, we have that command there. Our first argument, as always, is the key, and then we're going to add in members variadically. So in this case, we're going to add in, so we have tag 1 has article 1 and 3, okay? And that'll return back 2. Then we have sadd tag 2, so that's our key, article 3, 14, and 22. So we've added 3 here. And then we have sadd tag 3, article 9, 3, and 2. Okay. So you notice here, there's a common tag that you have between tag 1, tag 2, and tag 3. But at the same time, you've noticed that we've added them all in kind of different things. So there are 3 distinct tags, or 3 distinct keys representing tags in Redis. Now, let's say we want to see all the different articles that are tagged with tag 3. We use smembers, 9, 3, and 2. Now, I do want to take a small break and talk about what smembers is. So smembers is a ON operation. So it will take however many members there are that you have in that tag, it will return them all, right? So the smaller the larger the number, um, the more your results will be. But also it's uncontained. So you can't say, give me 5, right? So Redis can hold a very large number of members in a set, so it will sit there and wait and return everything. So be careful in Redis when doing operations that will return kind of an uncapped amount of data. So the key thing to know here is know your data. Something that's not in the presentation, but something to know if you want to, before you run something like that, you might want to run the command called scard or scardinality, and that will tell you how many members are in a given key. So in this case, if the number is 3, who cares? That's pretty easy to do so. But if the number is, let's say, 100,000, that's something that may not be something your application would handle very well. So keep that in mind. There are other commands like that in the database. You just have to be careful about doing those type of operations because Redis will say yes sir and give you that data back as soon as possible. So now let's look at a different thing. This is senter. Senter has doing a set intersection between 3 different keys. So we have tag 1, tag 2, and tag 3. And this will tell us what the commonalities, the intersection between those 3 keys are, or 3 keys are. In this case, we're looking at what is the common article in these 3 tags. We can see that article 3 is. And if we back up a little bit, we can see those are the bolded ones we had here. So easy enough. So I'm going to stop for a second, and then we'll do, after this explanation, you'll have another exercise. So in this case, what I want you to do is add the colors of the rainbow given here into this key called colors:all. Look around your workspace and find 3 different colors that you might have. So maybe you have white and gray and purple, and put those into a key called colors:workspace. Add your favorite color to the set colors:myfave. So maybe your favorite colors are blue, yellow, and green. So you'd add those to that. And then find any overlap between the 2 sets you created, workspace and myfaves. Again, we have a cheat sheet here. So pause the video here for just a few minutes and go ahead and do that exercise. Okay, I hope everything's all right. Should be easy. Let's go over this. The first thing we have here is we're adding the colors of the rainbow to a set called colors:all. That was pretty straightforward. Sadd, again, is that variadic formulation. So we've added the 7 colors there. Then we're going to use sadd again. And here we're going to add white, green, and purple to the key colors workspace. Again, with colors myfaves, green, purple, and gray, that returns 3. So senter will do the intersection between workplace and myfaves. And you can see here we have purple and green in those intersections. All here. Okay, let's shift gears again and talk about leaderboards. Now, leaderboards are great in a lot of different use cases, but gaming is one of the key things that you see people using it for. In that case, you have many users playing a game, collecting points, and doing all sorts of things like that. And you want to see who's ahead and who's behind and who's near you. This is something that we have sorted sets that are a great representation of this. And that's something that's really hard to do in a lot of disk-based databases because the data is constantly moving. So you can automatically keep the users by score, so you don't have to do constant sorting and that sort of thing. It becomes very easy to do so. We're going to use zadd to add or update, zrange or zrev range to get the users back out of that, and then zrank will get you the rank of any user instantaneously. So notice here that the z is actually what we'll be using here to represent a sorted set. So a z set sometimes is what it's called, but sorted sets is the proper term. Let's take a look at that. So here we have zadd game 1 with a score of 10,000. ID 2 is our member, our score, and then excuse me, our score member, score member. So we're going to do this kind of interleaving like we did with hashes, but we start with a score, and that's something a lot of people have a hard time with. But it's score and the member that we're adding. So we added 2 here, so we add those values here, so you can see the representation there. And then we're going to use zadd game 1, same key that we've been using before. 1400 is our score, a member, and then another member here. So we're using ID 3 and ID 4. So those have been added. So then we're going to use z anchor by. So we're going to increment that value, just like we used hinker by, but this is for a sorted set. And we're going to increment that score, right? So z incr by game1 is our key. And then the increment comes first this time. So we're going to add that value to ID3, which then changes it again. And it's going to return back just like hinker by returns back the new value that you have. Okay, so let's further work on this. Let's get the start and end. So in this, we use z rev range, so we're going to do reverse sorting. So we have our values there on the left, ID 3, 4, 1, and 2 with the scores. And we're going to use start and stop. So it's zero-based numbering, so we're going to get one value back out of this, right? So we're getting ID 3, and ID 3 has the highest value. So we're doing a descending order here, not an ascending order. Then we'll do zrev range, and we'll do 0 to 1, but we're going to have with scores. This is an optional argument to it that will return the scores back as well. So we can see ID3 and ID4 along with the scores, and it's interleaved, so you'll need to, in your application, decode that. So it's your turn now. So add 5 of your family or friends into the sorted set with their initials being the member and then their current age being the score. Find the commands you can use to actually find the youngest and then the oldest in your family. So go ahead and look at this. We have the cheat sheet right here. So pause your video and then we'll come back in just a moment and discuss what they actually mean. Okay, hope it was good. Let's take a review here. We'll use zadd. We're adding in those. So we have, again, that score member arrangement, and it's returning back 5 because that's the number we've added in here. And then we'll use zrange, family 0, 0. So we're getting the youngest member in the family, BD. This happens to be my dog, who's 10 years old. And then zrev range, we'll get the eldest in the list that I've added here. So pretty simple example, but you can do a lot with this. Imagine these are scores in a game or something along that size. Okay, now we're going to search by location. In this case, we want to do a geoset. We're going to plot things on the round world. And just a note, if you think the world is flat, the mathematics won't work out. It'll be off. So if you're a flat earther, maybe not the right data structure for you. But in this example, we want to find the pharmacies within a 2-kilometer radius of a given space, or how far I am from a hospital. These type of questions. Think about a store finder. If you want to find what are the stores nearest you that are selling hand sanitizer or something like that, you can be able to do that quite easily. So we actually use a thing called a geoset, which is a derivative of a sorted set. We'll get into that in a moment. And it uses a thing called a geohash to store that in the score, right? We'll see that in a moment and how that plays out. We'll use geoadd to add a location to the geoset, and then we'll use geodistance to get the distance between two, and then georadius to get locations in a given radius. So we specify a longitude and latitude, and then a radius, and it'll give us all the locations in the middle. Okay, so let's look how this works. We're going to use the command geoadd. We have our key is pharmacies, and everything in this will be under one key. We're going to do the longitude and latitude, and then our member name is there. Now, this is the most counterintuitive part that we have talked about all day long. Most people in the English-speaking world will specify things in lat long format. Redis is the opposite. So you're going to have to invert your coordinates from probably what you see anywhere written. Okay, so we have geoadd long lat. So that's going to return back 1. That's the one we added here. Now, if you look here on the left, this is the representation of that sorted set. We have that big number under Charles Henry Pharmacy, or Charles Harry Pharmacy. That's actually the representation of the geohash. So pretty interesting, but not very valuable to most applications. Then we have geoadd. Geoadd basically will add another value in here. We're going to use the same key pharmacies. We're going to add a Richmond pharmacy in here at a different location, and it's going to return that back. And we have that kind of nonsense number, which represents the geohash. And then we have geoadd for another time. So we've added 3 different items in. So we have 3 items in our geoset at this point. Now, let's go ahead and get things in a given radius. So we're taking georadius. Pharmacies is the key that we're looking at here. We have the long and the lat that we're specifying in that kind of weird inverted format. And then we're going to put the distance and the unit. Um, Geospatial Redis supports miles, mi, meters, m, kilometers, and feet. So really it's stored in metric system, but it's outputted as those for people who use feet and miles as well. We're going to specify with distance and with coordinates. So these are optionals, as well as a sort, which is optional as well. And so it can be ASC or DESC, just kind of like in some of the SQL query languages. So we can see here, the inside this radius, this 600-meter radius, we're returning back Charles Harry Pharmacy. It's 511 meters from the point that we specified, and then we have the coordinates here. Now, if you take a look back, we would look back here. Notice the coordinates we've put in here for Charles Pharmacy are slightly different than what's being outputted. This is something to know because basically what you have is it's a probabilistic structure, which means that we're not storing things exactly. We're kind of storing an estimation of that coordinate. It's pretty good. Think of it with about a meter or so accuracy. Don't build a self-driving car with it because it will be dangerous. Trying to keep it on the road, but it's good enough for finding things in like the middle of a city even. So it's pretty good, but you do need to know the limitations of it. We also see here that we have the coordinates. So that's this result of this optional argument with coordinates. And then it's stored in ascending order. Okay, now it's your turn to take a look at this. In this, we're going to do geo, where we're going to add a few values in. These 3 values in New York City. We're going to use geo add for this. And note the order of the longitude and latitude may vary in this particular exercise, so that is a little bit of a gotcha. And then what you want to do is find a radius of the given points in here within 1 kilometer, and what order should you visit them in logically, like going from the center out. What would be your logical order? So pause the video now, take a few minutes, and take a look at this exercise. Okay, how was it? Hope it was good. Let's review. So I've done this exercise for you. This is me doing it. First thing we're doing, we're adding all these places into New York City. We're using GeoAdd 3 different times here. And then what we're going to do is we're going to do GeoRadius with the correct order. So we're doing longitude and latitude, 1 kilometer with distance, and ascending order. So we can see that if we're looking at this in kilometers, Chrysler Building is 0.6 some odd kilometers away, top of the rock, and then Madison Square Garden. So this is how it's returning these things back. So I do want you to review a little bit and start thinking about, you know, how we started with get and set and how these have kind of gotten a little bit more complex as we went along, but it's all manageable. It's totally manageable. So one thing we also want to talk about today is how you're managing sending data to multiple places. This is something we didn't talk about yet, but Redis has another capability that's built in. It's called pub sub, publish and subscribe. In this example, or this type of thing, it's not really a data structure, believe it or not. It's actually a capability of Redis. It's not a data structure because the data is not stored on the server, which we'll get to in a moment. So imagine you have IoT devices, Internet of Things devices sending information back to multiple services, or you have an app sending out messages about activities on a social media platform or something like that. You want to be able to broadcast things effectively to multiple different places, and PubSub is the way to go with that. You have a way of sending messages to the server, and the server being able to distribute those back out without actually storing them. So you don't have to poll. Basically, what you do in this is you just say, I'm subscribed to this, and then asynchronously, information will be returned to you as it comes along. Use publish to publish messages, to send them out, and then subscribe to get messages, right? So let's take a look at how this works. In a PubSub server, you have a situation where you have like a topic subscription. So you say, I want to subscribe to a particular topic, and then I'll get all the messages on top of that. And the key thing to know about this is that it's fire and forget. What is fire and forget? Fire and forget is this idea of being able to fire the message off, but not actually hold it. So if somebody is offline, there's no way to retrieve anything that they're not there to receive. So it's not durable or persistent, right? So keeping that in mind as you start publishing things out to Redis, if somebody goes offline, they won't be able to recover and get that message back out. Okay, so here's our example. Imagine we have 3 different machines or 3 different terminal windows even that we're doing things, and there are these boxes on the screen. Now, first thing we're doing, we have one that is connected to a centralized Redis server that says, subscribe to the weather in Stockholm. It will display this message saying, hey, I'm subscribed to one thing, and this is the channel that I'm subscribed to, weather in Stockholm. Now, on a different machine, we are subscribed to the weather in Stockholm and the weather in Madrid. And we get a message back saying, okay, I'm subscribed to 2 different things. At this point, no problem. So they're just sitting there idle for however long it takes. Now, up top, we published the weather in Stockholm is 7 degrees Celsius and cloudy. Now, you notice both of the ones below were actually already subscribed to that, so they're both receiving that message. Now, I'm going to publish the weather in Madrid, which is 36 degrees Celsius and sunny. And you notice the red box is the only box which actually was subscribed to that. So the blue box is still waiting for messages to come in. So it becomes very easy to see how you could use this to distribute things out. So imagine this might be as things processing things on the weather, or IoT devices saying, oh gosh, I need to turn the lights on when it's too cold, or something along those lines. Now, the final thing I want to talk about today is how you actually use Redis in your application. So we talked about Redis CLI a lot today and Redis Insights, but how do you actually build this into something useful? So Redis is a bit like a Rosetta Stone of software. It has a very simple API that can be articulated in many different languages. So in this case, we try to make sure that we follow the idiomatic language constructs as much as possible, but what we really want to stay true to is the commands in Redis. So let's take a look here. 4 different languages. If you notice, they're going to look an awful lot alike. So we have Node.js here. We're going to add to a sorted set. We're doing key and then the score and then the member. We learned that earlier. Python is the same thing, but we have a slightly different way of articulating it. It doesn't have a callback in this case, which is kind of a Node.js thing. Java is working the same way as Python. I mean, they're practically after the Redis versus Redis client. It's the only difference there. And then everybody has to have something that's a little bit different. Of course, then we have C# here with Redis.sortedSetAdd, but the arguments are all the same. So keep that in mind. It's articulating zadd, it's a sorted set add. They're kind of equivalent. This can be something that can be really similar across different languages. In fact, you could learn a language. If you know Redis very well, you load up the Redis client, you'll probably learn how the language works. Well, that's it for today. I want you to stay in touch with me. You can find me at Stockholm UX. My GitHub is the same thing. It's a long story on why that's my handle online. I'll share it with you sometime, but not right now. And you can certainly email me, Kyle at RedisLabs.com. Thanks, and make sure to show up to the Q&A.